So in this video, we're going to consider the first case, which is our dielectric-dielectric boundary. And so to sort of take a step back, we know we're talking about some electric field which is applied across this entire material. So maybe we have, some E field line that is going like this more or less, and again, it's across this whole region. But we're going to have slightly different direction, slightly different magnitude, depending on which region we're in. And so what we're wanting to do is then to relate our electric field in region 1 to our electric field in region 2. And so I've sort of already set up a couple items here, and we'll talk about those and then set up an additional item as well. So we see in sort of the top half of this region, we have our region 1, we're going to call it, which has a permittivity of epsilon 1, which is equal to our epsilon naught times the relative permittivity epsilon sub r1. In the bottom, we have material 2, which has permittivity epsilon 2, which is our epsilon naught times the relative permittivity of epsilon r sub 2. I've also gone ahead and labeled our epsilon 1, our E1, our electric field in region 1, and our E2, our electric field in region 2. And so notice I've already sort of got these right triangles such that we can go ahead and break these down into their normal and tangential components. And remember, normal and tangential to what? To our interface between the two regions. So let's go ahead and label these. So if we're looking at E1 up here in the top, this is going to be our normal component of 1, so let's call this 1n, and this is going to be our tangential component of 1, let's call it 1t, and again, that's normal to our interface and tangential to our interface. Similarly down here for our electric field E2, we have some normal component, E2n, and some tangential component, E2t. All right, so that's always going to be our first step, is to sort of decompose those. And ultimately, we're going to see we don't have to do this every time. We're going to arrive at sort of a simple equation. So first, in order to relate these electric fields, we want to apply one of the equations from the previous notes, which was our integral along a closed path of our electric field dot dl is equal to 0. And so in order to do that, we need to come up with some path here. And so if we're trying to relate the electric field in these two regions, we want a path that goes through both of them. So let's have a nice square path that's going to be easy to deal with, or a rectangular path rather. And let's put that right there so it's sort of part in each region. And so let's sort of arbitrarily say we're moving clockwise around this path. And to make things easier, let me go ahead and label our four corners here. So let's say this is A, B, C, D. So we're going to move along the path A, B, C, D, A. So let's do A, B, C, D, A. And so one other thing we also need to do to sort of simplify here is let's assume that the path is small compared to spatial variations of E. So assume our path is small due to spatial variations of our electric field. And so ultimately what that means is that, if we're going from A to B and, that's a lot smaller than any spatial variation in E, then along that path, our E is essentially constant and we can pull it out of the integral. So we can pull our what we're going to call constant out of our integral. Okay, so now we can consider doing this path. So for our first sort of segment there from A to B, again, if we're pulling E out of the integral, we're just going to have some constant E1, and so that's going to be our E1t, because our dl is going to be in this direction, right? And so here our dl is going to be in this direction, here our dl is going to be in this direction, and here our dl is going to be in this direction. So there's our 4dl. So if we're looking at that AB segment, we see that our normal component of E is 90 degree different from that. So that's going to be, if we do the dot product, that's going to be 0. So the only non-zero term is going to be our E1 tangential dotted with dl. Those are both in the same direction. So the dot product is just going to be 1. So looking at our integral here, we pull E out of the integral, so that's just going to be E1t. and we have the integral over this path, so basically that's just the length of the path, which is going to be the width. And so I didn't label that, but let me come back here and say that we have some width of this box, which is delta W, and some height of this box, which is delta H. All right, so along that first path then, we just have our E1t, because that's the only component that is in that same direction as dl, and then the length of the path is just going to be our delta W. All right, so now for the second part, we're looking at this path BC. So we're going here, and so we're going to have to split this up into two parts, because of course in this first part here, we're dealing with our electric field 1, and then with our second part, we're dealing with our electric field 2. So for electric field 1 in this region, again, we can see that we have one component which is going to be in the same direction, or in this case, negative 180 degrees. So it's sort of, our dot product is going to give us negative 1 in this case, and our E1t is 90 degrees off, so that's going to be 0. So we're just considering our E1 normal. Again, because it's in the opposite direction, we have a negative sign from our dot product, but we pull that E out because we're assuming that it's small. So we get our E1 normal, and then the integral of that path is going to be half of our delta H. So coming down here, we have minus E1 normal times delta H over 2. So similar idea here. Now in this area, we're going to consider our E2 normal. It's in the opposite direction of our DL, so we're going to have a negative sign as well. We're still considering that E2 normal to essentially be constant along that path, so we pull it out of the integral, and we're going to end up with minus E2 normal times delta H over 2. So let me go ahead and move this over a little bit so I have enough space, hopefully. Okay, so now we're just continuing along this path. So now we're looking at our CD portion. And so we can see again, the only component that's going to sort of result in a non-zero term is our E2 tangent. Our E2 tangent is in the opposite direction of DL, so that means we're going to have a negative sign again. So we're going to have negative E2 tangent. We pull that out of the integral, and so we get a negative E2t. And then the integral over that path is just going to be the width, delta W. All right, so then finally we have two more segments to consider. First, this path in our region 2. So we see now our DL and our normal component of 2 are in the same direction. So that's going to be positive now. So we have E2n, and then the integral over that path is delta H over 2. And then finally, our last segment before returning to A is sort of in this region 1 along this direction. And again, now our DL is in the same direction as E1n. So coming down here, what we're going to have is plus E1n times delta H over 2. All right. Now, we need to sort of keep in mind, we said that overall, if we're doing a closed path, that has to be equal to 0. So let's set this equal to 0. And so what we can see is we have a few terms that are going to cancel out. So this one is going to cancel out with this term, and this term is going to cancel out with this term. So we're just left with these two terms here for those sort of horizontal paths as they're shown in the figure here. So from A to B and from C to D. So if we sort of simplify that, the delta W cancels out, and we're left with E1t is equal to E2t. And so that's saying the tangential of our field in region 1 is equivalent to our tangential in the field in region 2. So the tangential component of E is continuous across the boundary is what we would say. So tangential component of E, which we've labeled as E sub t, is continuous across the boundary. Okay, and so that's very important. So tangential component of E, continuous across, and so let's see if I can actually spell correctly. So, nope, there we go, across the boundary. All right, so we could also talk about what this means for our electric flux density. So of course, remember our electric flux density is equal to our E times epsilon. So we could say our D1 of T divided by epsilon 1 is equal to our electric field 1 of T. And so we know electric field 1 of T is equal to electric field 2 of T. So our tangential components of electric field are equal, and our electric field 2 is equal to D2 divided by epsilon 2. So from this relationship, of course, we know that our epsilon 1 is not equal to epsilon 2 in this case. So that means that the tangential component of our electric flux density, d sub t, is discontinuous across the interface. Yeah, just really having trouble spelling across today for some reason. So across the interface. And so again, as I mentioned at the start, we're not going to have to sort of go through this derivation each time, but instead we're just going to come straight to this relationship of our tangential component of electric field is continuous. And in the next video, we're going to see how we can relate our electric flux density across the two regions as well. And so with those two pieces of information, we then know how to relate our fields in region 1 to our fields in region 2.